Okay, good morning, everybody. Okay, last class it appeared we went through a lot of material, and I just want to reiterate a couple of things. A lot of the stuff, and what you will find at the beginning of a chapter, we kind of go through what looks like a lot of material, but a lot of what we go through we've either covered or we will be covering in greater detail in the upcoming chapter. It's kind of an intro, and typically the way we introduce new functional groups, and although this isn't a new functional group, this is the chapter that has the next couple of chapters which really deal with aldehydes and ketones. We talk a lot about how we might make them, and so a lot of those reactions will have been covered before, and then some of them, for instance this one where we made a ketone by reacting something like a Grignard reagent with a nitrile. We'll actually be covering what goes on from here to here a little bit later in this chapter, in this section. So that was the last reaction we had, was how to make a ketone by reacting an organometallic reagent with a nitrile. And nitriles are kind of similar to ketones in that we have a carbon bonded to a heteroatom with multiple bonds, and we can draw resonance structures, but the carbon is electrophilic there as well. If we look up in the periodic table, we see nitrogen is to the right of carbon. So this is an electrophilic carbon, and that's the carbon that will be attacked by the organometallic compound to form this intermediate. And we're going to see something that looks like that, if not today, then on Friday, and how that actually gets converted to a ketone. So here we can see we can make these different ketones. Notice 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That framework came from here, and at the end we kind of switch out the nitrogen for an oxygen. This methyl group came from our methyl lithium. The same thing here. We add this vinyl group to that carbon, and there we go, there's our vinyl group, and we switch out the nitrogen for an oxygen. So we're just clipping together those molecules. Then we like to remind you of your arsenal of reactions that you're learning. Here we say suggest a synthesis of this compound from these two starting materials. Now one of the things you might think of right away, well, what if we oxidize this to a aldehyde, and then we can add the Grignard reagent to the aldehyde, making an alcohol to clip these two together and then reduce it, but count the carbons. This is easy to see in the product. Then count our carbons here, 1, 2, 3, 4. We have 4 carbons, 1, 2, 3, 4. We need another carbon. We actually need 5 carbons in this molecule. So we have to add a carbon. Now, we're reaching back to things that you did last semester. So we have 5 carbons that we need to add. We only have our phenyl ring and our 4 carbons. We need to add a carbon. We need to reach back to last semester, and we can add a carbon by displacing an alkyl bromide. We can just do an SN2 reaction where we knock off that bromide and add this thing. Not only do we add a carbon, well, we get that nitrile functionality that we need to go ahead and perform the rest of the reaction. So a retrosynthetic analysis, we're just working backwards. We realize that we can make this, we can disconnect this thing here, and we can make that from these two compounds, but we don't have that. We can make that from this, and we can make this from the alcohol, and that was one of our starting materials. So that's the retrosynthetic analysis. The final, oops. So our final synthesis then, we have to reach back. How did we convert an alcohol to an alkyl bromide? We used phosphorus tribromide. Then we can react the alkyl bromide with sodium cyanide, and we just do an SN2 reaction, and finally we work it up. We do the reaction with the Grignard followed by a workup to, we get the Oh, this is actually wrong. This would give us the alcohol, and the alcohol then has to react with PCC or something else to oxidize. So there's a mistake in that slide. Our initial this should come immediately after that arrow, and then we follow that up with something like PCC or some other oxidizing agent to oxidize this compound to the ketone. So here's a different suggested synthesis. Now we have the right number of carbons, 1, 2, 3, 4, 5, and we need 5. So we want to just think about retrosynthetically. All we have to do is connect this carbon to this carbon. We can't do it with the alcohol. We've been learning about Grignard reagents, so we just kind of do the same thing. We take our retrosynthetic analysis tells us that we can make these two compounds by clipping them together. There's some stuff in between. So we do our disconnection. We get this reagent and this reagent. However, we can add that to get to there. We have to start from here, though. So we have to now think in the other direction. We take our alcohol. We oxidize our alcohol to get the aldehyde. We have to use PCC because we can't use Jones reagent because that would go all the way to the carboxylic acid. We then take our phenylmagnesium bromide and we react it with the carbonyl carbon, work it up in acid, and we get this alcohol, which we then finally oxidize to get to our final product. So you're now beginning to start thinking about these things as puzzles. And I don't want you to be too concerned. Are you going to have to know reactions from last year? Periodically, yes. But most of your quizzes and your midterms and stuff will involve the reactions that we learned this year. Periodically, there may be some reactions. Here's a hint. If you know you have to if you have an alcohol and you need to get added carbon and get to the nitrile with the added carbon, and you can't remember how to do that, at least just do the arrow there and say, I know how to do this. There's reagents that will help me out, and you will get most of the marks in the grand scheme of a total synthesis, okay? So when you're doing a total synthesis, if you can't remember the exact reagents for one step or two steps, you're still going to do okay on the question. Just indicate that you know you have to go from one compound to the next, and that you know there's ways of doing it, and you just forget the specifics, especially if it comes from last semester. And having said that, most questions won't have a lot of reactions from last semester, except perhaps in your homework assignments, okay? And then you have everything available to you. Oh, by the way, I will increase the number of tries on sapling from 2 to 3. Okay, so we've already talked, these, by the way, this should be a delta negative and that should be a delta positive. MAC doesn't always work well with others. So these are older slides. The nucleophilic addition to the carbon-oxygen double bond, we've actually been introduced to it, but our nucleophiles react with the carbonyl carbon. One of the things we want to remember is that this structure is planar. This, the carbonyl compound and its adjoining two atoms over here are all in the same plane. When we add our nucleophile, then our nucleophile can come from the top or it can come from the bottom, and that's going to have some consequences. The consequences are that, this is just explaining. Remember these resonance structures, and this is why this carbon is electrophilic, is due to the electronegativity of the oxygen, and we can kind of draw a resonance structure, not a real good resonance structure, which shows the positive charge on the carbon. We could draw another resonance structure. Instead of moving our electrons up here to get that, we could move our electrons down and draw a resonance structure with a negative charge in carbon and a positive charge on oxygen. Why is that a bad resonance structure? A worse resonance structure than this one? think back to first year. Where do you want the negative charge? If you have two different atoms and you want to draw a resonance structure with a negative charge on one of those atoms, where is it going to be? The more electronegative atom. That's correct. So that's why that other resonance structure is not a good contributor. So the general reaction, then notice we have this thing which is planar, and we add some nucleophile. We have here a protonated nucleophile. Our compound goes from being sp2 hybridized to sp3 hybridized. What else do you notice about this particular carbon? What would we say about it? The fact that it has 4 different groups attached to that carbon. It's chiral. So we talk about these groups as being prochiral. And if we want to introduce chirality to a molecule, we have a way of now doing it. Most reactions, though, you have to go through special conditions, which we're not really going to get into in this course. But you can make chiral compounds from prochiral compounds, but you need something to induce that chirality. If we just do this reaction in solution, we're going to get an equal mixture of the two enantiomers. So we'll get a racemic mixture. We have to go to added conditions to induce that chirality. But for right now, I just want you to realize that that is possible. So we have a nucleophile, and that's our general mechanism. We have 2 ways that we can do this particular reaction. We can use a strong nucleophile. And typically when we think about strong nucleophiles, instead of having the protonated form, we have the unprotonated negatively charged nucleophile. So we have our aldehyde in this case, and we have some nucleophile that's negatively charged. This is a strong nucleophile. Might be hydroxide, might be an alkoxide, might be something that has a negative charge. That's what this is supposed to be. That's a negative charge. And we just push our arrows. We attack the carbonyl compound. Okay, so in this case, our nucleophile started off with a negative charge. The pair of electrons that were the lone pair, it owned all by itself. It attacks the carbonyl carbon to form a bond. We promote electrons up to oxygen. Notice now our negative charge is up on the oxygen, and our nucleophile, which was negatively charged, is now bonded to the carbonyl carbon and is itself neutral. The other thing that's important is this step is reversible. It's an equilibrium. And what happens now is going to depend on what happens to this thing. And quite often what we can think of doing, I'm going to put, okay, we have more of our nucleophile, the NUH, so we started off with strong nucleophiles, so we have to do this under slightly basic conditions. We started off with a strong nucleophile Nu minus. We add and we get this thing which we call our tetrahedral intermediate. In this case, it's a little bit deceiving because our tetrahedral intermediate goes on to give a tetrahedral product in this case. What we will find in the next chapter is that this tetrahedral intermediate has other options depending upon what else is bonded to it. So in this case, our tetrahedral intermediate just acts as a base and pulls off a proton from our protonated nucleophile, acting as an acid, to give us our compound, which looks something like an alcohol. What it is in particular depends on what that nucleophile is, and regenerates another strong nucleophile, which can then go and attack another carbonyl compound. We can also do these with weak nucleophiles. And when we use weak nucleophiles, we tend to need to activate these compounds. We activate them with a small amount of acid. Either Bronsted acid, some source of H+, or maybe a Lewis acid, which is just some positively charged metal cation that can coordinate to the oxygen. But what this in effect does, I'm going to, you guys don't like that. There we go. So we protonate the oxygen. Okay, now over here we have our protonated oxygen, and I'm just going to draw these resonance structures. What we have in fact done is activated the carbonyl carbon. We've activated it because now it's a much better electrophile. We now have something that has a full positive charge rather than that previous resonance structure that we had up here. Although we draw on a positive charge of the carbon, we also have a negative charge on the oxygen. Now our compound is fully positively charged, so it's a very good electrophile. So we talk about activating the carbonyl carbon. We've activated it so that it can now be attacked by a weak nucleophile. And we can just push our arrows Now, one of the things you want to remember when you're doing reactions under acid catalysis, once you protonate, you've got a positively charged species. Most of the time you're going to be dealing with positive charged species or neutral species. Okay, so be careful if you end up with negatively charged species under acid catalysis. You've probably done something wrong, although rarely we might see that. But most of the time if we're under acid catalysis, our reactive species are protonated and positively charged. So we still have a positively charged compound here, and whatever our conjugate base was is going to end up pulling off that proton. So whatever acid we used, it had a conjugate base. Now there's other things that can act as conjugate bases, and we'll talk about that later today. So all that happens then we now have our source of a proton, our acid, which here I didn't show it as being an acid, but we just remove a proton. We end up with the same compound. We end up with our tetrahedral product. So we can do it with strong nucleophiles, in which case our nucleophile is probably negatively charged. It doesn't have to be, but it probably is. You can figure out the mechanism if we have what we consider a strong nucleophile that's positively charged, it'll look more, or I'm sorry, that's neutral, it'll look more like this, but we get the same product, okay? So the next couple of slides we just did on the board, so we don't really need to go through them, but one of the things I want to reiterate is that our nucleophile can attack from the top or the bottom, and that will dictate which enantiomer we get. Now, barring everything else, it's just as likely to attack from the top as it is to attack from the bottom, so you should get a racemic mixture. What you really need to do is coordinate it up, tie it up so that only one face is accessible, and then you can get an enantiomeric excess. With the weak nucleophile, the first thing we need to do is activate the carbonyl compound. Once that's activated, it's reactive towards weaker nucleophiles. So we've seen this reaction. This was a case of a strong nucleophile, right? And we talked about our methyl group being very much ionic in character. We get this intermediate, and then we have to work it up in this case. In that case, we didn't necessarily have to work it up. Our proton sources are there. In this case, it stops here. This thing is stable under the conditions that it's in, but whether it's stable or not is going to depend on what the three groups attach to the carbon that is attached to the negative charge. We'll see that. So we get stable isomorph products. Sometimes, in this particular case, here we have a weak nucleophile, methanol, and under acidic conditions, and we form our first product. This thing may go on to create other things. That is, it may not be particularly stable, and it may want to do further reactions. So we're going to see a couple of cases of each of these. Now, as I'm erasing, you guys can read that, but one of the things that's important you have to remember is the reversibility of nucleophilic additions to the carbonyl carbon. Oftentimes we forget to draw our equilibrium arrows, but we always have to be aware that to a greater or lesser extent, all reactions are reversible, but this happens to be one that is usually easily reversible. So these reactions are very much dominated by equilibrium. And we usually have to do things to get them to go in one direction or another. And we'll get into that in a little bit. But let's talk a little bit more about the relative reactivity of aldehydes and ketones and esters. So if we take a look at these two compounds, we've already alluded to the fact that if we have this compound versus this compound, which one of these would be more sterically accessible? My aldehyde or my ketone? How many people think this is more sterically accessible? Okay, and we've tried to emphasize that by drawing our tiny little hydrogen. Okay, so aldehydes are more reactive than ketones for steric reasons. Now the other thing that's interesting, remember that we have that resonance structure which contributes greatly. The other thing is that, do you guys remember back last class when you talked about the stability of carbocations? What were the most stable carbocations? Primary, secondary, or tertiary? Tertiary. Why were they more stable? That's right. Alkyl groups are electron donating. So if we alkyl groups are electron donating. So if we want to think about this particular resonance structure, that's just indicating, actually let's not do it that way, although your textbook does, I prefer Both alkyl groups are pushing electron density towards that positive charge and stabilizing. The partial positive center. And in the case of oh, we can leave that. Remember, we talk about them being electron donating relative to hydrogen. So in this case, we only have one electron donating group to stabilize. This partial positive charge. Well, actually, the way I've drawn it, it's fully charged, so we don't need those. Okay, so both electronically and sterically, alkyl substitution makes the carbonyl carbon less reactive, so that this is less reactive than this for both steric and electronic reasons. For a similar reason, esters we can draw a resonance structure which further stabilizes the carbonyl carbon and makes it less reactive towards nucleophiles. So esters, for electronic reasons, as well as steric, but are less reactive even than ketones. So the carbonyl group in an ester is less reactive than the carbonyl group in a ketone. Now, we will talk about esters much more in the next chapter, so we're going to kind of forget about that. So this is just reiterating that steric and electronic factors. Okay, this is what we've done on the board. Now let's talk about our nucleophiles. Here's a weak nucleophile. Our nucleophiles we drew like this. Okay, so here's a weak nucleophile. What is this compound? H2O, water. Okay, water is a weak nucleophile, and water reacts with aldehydes and ketones in what we call a hydration reaction. And here we have the reaction here. It's very much an equilibrium reaction. Okay, so thinking back to what we just discussed, this is very much an equilibrium reaction. We have substituent effects on this equilibrium. Aldehydes are going to favor hydration versus the carbonyl compound, and ketones are going to be less reactive and also less stable, and ketones will be much less likely to exist in their hydrate form. So the first step in the reaction, we can do this under base or acidic conditions. Under basic conditions, we have the case of a strong nucleophile reacting with our carbonyl compound to form this alkoxyl anionic type of intermediate, right? And this thing is just going to remove a proton from water to form our hydrate and then reform the nucleophile. So we talk about this as being base-catalyzed hydration, okay? And this is, we add OH and then H, so we've added water across that double bond. We can also do this reaction under acidic conditions, in which case we throw some acid in there, and in aqueous solution, acid will be, the proton carrier will be this hydronium ion. It will just protonate the carbonyl oxygen to activate our carbonyl carbon. So the first step is the activation of the carbonyl carbon by protonation on the oxygen. Then we get our nucleophilic attack of the carbonyl carbon to form this thing. Notice this thing looks very much like this, and all we have to do is remove that proton, okay, just like we did in the general mechanism. So our conjugate base, in this case water, comes along and pulls a proton off to form our hydrate and reforms the acid. So the acid is a catalyst in this case. So for hydration, we can have base catalyzed or acid catalyzed. Under basic conditions, we have a strong nucleophile doing the initial attack at the carbonyl. Under acidic conditions, we have to activate our carbonyl, which allows the weaker nucleophile of just unprotonated water attacking the carbonyl carbon. So as I mentioned, this is, take a look at this chart when you look at your notes. When we're talking about relative rate, this is what it's relative to, which is acetaldehyde. Okay, so acetaldehyde exists almost 50%, it's actually slightly greater as the hydrated species in an aqueous solution. So if we take acetaldehyde and put it in water, about half of it is going to be the hydrated form of acetaldehyde. If we take formaldehyde, which we think about as being very soluble in water, it's actually not soluble in water, it's very reactive with water, it gets hydrated. Formaldehyde is greater than 99.9% in the hydrated form. Acetone, which we think about as being very miscible with water, mixes in all different degrees. Acetone down here actually exists almost entirely in the acetone form. Okay? So this coincides with what we talked about in terms of the reactivity of aldehydes versus ketones. And notice now when we start bulking up this group, even though this is more electron donating, it's getting quite bulky, and it exists much less so in the hydrated form for this thing, which we might call it's a propanal, 2,2-dimethylpropanal. So 2,2-dimethylpropanal exists primarily as the carbonyl compound, but there is a significant portion of the hydrated compound. Now don't worry too much about this. This isn't particularly useful for anything in terms of synthesis, but it is important to understand these are all equilibrium reactions. So for this particular reaction, we could drive this completely by not having very much water around. If we put it in a dry solvent, it's not going to be hydrated. So again, by putting electron donating groups, we favor the ketone. By putting electron withdrawing groups, we very much favor the hydration. And this is an extreme example. We've replaced our methyl groups in acetone, which acetone exists primarily as acetone even in water. If we replace those with trifluoromethyl groups, and we look at fluorine, fluorine is the most electronegative of elements, so the trifluoromethyl group is very electron withdrawing. And now when we do that replacement, we see that our equilibrium constant goes way up, and hexafluoroacetone exists primarily, almost exclusively, as a hydrate in aqueous solutions. Now, so we talked about our nucleophile, and we talked about HOH. What about ROH? It's just simply an alcohol. So alcohols react with carbonyl compounds in what fashion similar to water. So this first step, we could do these under acid catalyzed conditions to make this thing That's the equivalent of making the hydrate, only we've reacted one molecule of alcohol with our ketone compound to get this thing we call a hemiacetal. And it's a hemiacetal because it has an RO and an OH on the same group. As it turns out, this is now a case of one of those species that is reactive and doesn't like to stay there. It will react with another molecule of alcohol to form this thing which we call our acetal. And our acetal has on its carbon 2 alkoxyl groups. Okay? So a hemiacetal has an OH and an OR group bonded to the same carbon. An acetal has 2 OR groups bonded to the same carbon. And although we won't get into it here, an orthoester has 3 OR groups bonded to the same carbon. Okay, so those are 3 different functional groups. Now, this particular reaction is catalyzed by acid. We can do this reaction under basic conditions, but it has a tendency to stop here. But under acidic conditions, it'll go all the way to here. Notice, though, it's all under equilibrium conditions. Now, one of the things I kind of want to warn you about, for those of you who haven't bought the textbook, which, by the way, I think you're better off with a textbook, even though it's a few $100, but if you're taking 2 courses, it gives you something to refer to. So aldehydes react with alcohols to give a hemiacetal, which will react with another molecule of alcohol to give an acetal. Ketones do the same thing, but what you may find in older textbooks and a lot on the internet is that there's an older nomenclature term. Ketones make ketals and aldehydes make acetals. And the only difference is with acetals there's a hydrogen bonded to that carbon. And with ketones there is no hydrogen bonded to that carbon, which has the OR groups on it. Okay, so you may find that. Most modern textbooks have gone to calling both of these. They no longer distinguish between the two. You will find older textbooks, and particularly biochemists and medicinal chemists kind of hang on to this old nomenclature because biologically ketals would have different biological effects than acetals because quite often shape is very important and they have quite different shapes. So let's think about the mechanism for this reaction. Now this is a good example. So we're going to just take some ketone and I'm going to take an aldehyde and I'm going to react it with methanol. Okay? But the first thing that has to happen is the protonation. In water, when we throw an acid in water, what carries the protons around? What's the species that does the protonation? Water with a proton attached becomes the hydronium ion, right? H3O plus. In aqueous, H3O plus is kind of the proton shuttle. In methanol, one of our hydrogens has been replaced by a methyl group, and that is our proton shuttle. Okay? So that's something to be aware of. When we talk about H plus doesn't exist by itself. If we might do this reaction in methanol, and we would add a little bit of acid catalyst, and our proton shuttle is going to be the MEOH2. Okay, that's our proton shuttle. But we're not really going to worry about it because we're just going to call it H+. What I'm trying to get across there is, remember, something is shuttling that H+ around. So the first step in the reaction is activation of our carbonyl group. Okay? Activation of our carbonyl group. Now I'm introducing the methanol. And our methanol is going to attack that carbon. Oops. Right? I just want to erase this now. Another molecule of methanol . Okay, so there, our proton shuttle just removed a proton. We may, instead of showing that actively, what you may say here is minus H plus above that arrow. Also want to remember that we have. So this thing is our hemiacetal. So your slides are trying to kind of convey that by showing this first step. They're just protonating the alcohol, and then the alcohol is the proton carrier that's protonating the carbonyl oxygen, which is activating that compound. Okay? We now get our, at the end of this equilibrium, we have this acetal, hemiacetal. Our hemiacetal, I'm going to bring it all the way down over here now. Our hemiacetal . Now I'm going to go back to just, I have a tendency to just put H plus there because otherwise it takes too long. So we can now protonate our H plus. We are going to want to get rid of some water here. I'm just going to put a line here. There we go. Okay. We've now protonated our hydroxyl oxygen. And we can just knock off, these are pairs of electrons, and knock off a water molecule. Okay, this thing, now we have this oxonium type of thing. We could draw a resonance structure which takes that positive charge, puts it on there. That has an electrophilic carbon, and we have a nucleophile around. What's the nucleophile we have around? It's a weak nucleophile. Oh, what else does this do? I'm going to put it in a box too. Molecule of water came off here. So now we're going to add, we're not adding it. Let's just say, still there. There's still lots of methanol. Methanol is our solvent. So whenever we need a methanol, we just grab it because that's our solvent. Pardon? What did? The methanol. Methanol is our solvent. Oh, okay. So we have lots and lots of methanol around. Whenever we need one, we just bring one in. Okay? So our methanol then is just going to attack that electrophilic carbon. Oops. Sorry. Okay. This now becomes neutral. That oxygen becomes neutral. And all we have to do at the end, and I'm just going to say minus H plus here, to give us our RCOME plus H plus. So that was our catalyst, right? The protons jump on and jump off and jump on and jump off. Now, one of the things you want to remember is that all of these are equilibrium reactions. All of these are equilibrium reactions. The proton is jumping on and off all over the place. When it jumps in the right place, the next reaction can occur to eventually get to here. How would you So our overall net reaction then you really should try this mechanism out. Write it out on a piece of paper. It's in your textbook. It's on the slides. It's all over the internet. But you should practice this particular mechanism. A lot of mechanisms are very similar. But our overall reaction then is 2-methanol plus an aldehyde catalytic amount of H plus to give us what's our other product? Does anybody remember? Water, which we put in the box up there. Okay, and this reaction is an equilibrium. Now we did this reaction in methanol. We can use any alcohol to do these reactions. If we wanted this as our product, what might we do? Remember back in first year, remember all the way back to something called Le Chatelet's principle? So if we wanted this as product, we would do something to get water out as it forms. And that will drive the reaction to here. What if we started here and we wanted to go this way? Well, we just throw in a whole bunch of water and we can make the reaction go the other way. So remember Le Chatelet's principle. These are all just the mechanism. So all steps are reversible. In the presence of large excess of anhydrous alcohol and a catalytic amount of acid, the equilibrium favors the acetal. If we have much water present, the reaction will favor the aldehyde or ketone. So we can drive the reaction the other direction just by doing it in the, just by taking our acetal and adding some water and some acid. Now, next class we're going to talk about intramolecular hemiacetals. So if we have an aldehyde and somewhere on the same molecule we have an OH group, we can have an intramolecular reaction occur where this is our nucleophile. These reactions tend to go very easily because they're always bumping into each other, and every once in a while they form a bond. So you don't necessarily need an acid catalyst, but an acid catalyst would make it go further because the alcohol portion can't diffuse away. It's always right there ready to react. And in fact, with 5- and 6-membered rings, the ring formation is very favored, and then we just have to get a proton moving from here to here, and there's lots of things that can shuttle that proton around to form this cyclic hemiacetal. The reason they're important, so hemiacetals, remember, have an OH and an OR group. Why are they important? Does this look familiar to anybody? So it should, okay? So for those of you in biochemistry, glucose exists primarily in the form of a hemiacetal. I apologize, I wanted to have your quizzes ready for today.